So let's consider a multi-electron atom. You have more than one electron. So again, we have a nucleus and it carries charge positive Z. Here I'm using atomic unit, so I do not write E, right? E is equal to 1. So you have here a electron, electron 1, here another electron, electron 2. Let's just draw 2 electrons. So in this case, again, we put the origin of our coordinate on the nucleus. So you will have 2 vector here, R1 vector, right? This is R1 vector. You have the R2 vector. This is R2 vector. And you have a distance between 1 and 2. So you can have a R12 vector. Right? Now, what is the Hamiltonian? The Hamiltonian is equal to, well, this is what I draw here is 2 electrons, but in general, I meant to draw a many electron system. So this is going to be a summation from 1 to n. I here is the index of the electron. Capital N is the total number of electron. Okay, and for each electron, you have the kinetic energy part. The kinetic energy part is in atomic unit is -1/2 Laplacian for the ith electron. So you will do partial derivative with respect to the position of the ith electron. Minus, you will have an interaction between the nucleus and this electron. This is Coulomb attraction. This is -Z over Ri. It depends on the position of the electron, of the ith electron. Okay. But do not forget, you have electron-electron interaction. You have electron-electron Coulomb repulsion. Repulsion potential is positive, right? You need to plus an additional term. And this electron-electron repulsion is 1/Rij, right? It depends on the distance between 2 electrons. 1, 2, then it's R12. 1, 3, then it's R13. However, the R12 potential is equal to R21, right? You cannot count the same pair twice, otherwise you are double counting, right? That is, the Coulomb interaction between 1, 2, which is 1/R12, is equal to the Coulomb interaction between electron 2 and electron 1, which is equal to 1/R21. You can only write down this term once, otherwise you are double counting the Coulomb interaction. So by writing a summation here, we specify I must be smaller than J. This means when you do the summation, you only do 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, etc. You do not do 2, 1, 3, 1, 4, 1, right? You eliminate half of the summations. You eliminate half the term in the summation because you do not want to double counting the Coulomb interaction. Okay, this is a very important point. Of course, I cannot be equal to J. There is no R11, right? What does that mean? Electron interact with itself. In the exact theory, in the exact Schrödinger equation, an electron does not interact with itself. Okay. The Coulomb repulsion is always for a pair of electrons. Okay. So Rij is the magnitude of the Rij vector. This is equal to the location of I minus the position of J electron. Okay. Sometimes people write this summation I smaller than j, 1 over rij in another form. This is equivalent to 1 over 2 summation I is not equal to j, 1 over rij. This is equivalent, right? You just eliminate half of the terms in the summation. That's it. So you can either write the left-hand side expression or you can write the right-hand side equation. When you use I is not equal to j as the index for a summation, do not forget to add a factor 1 over 2 in front of the summation to avoid double counting the Coulomb repulsion. Okay, this is the notation. All right, then of course, we know the Hamiltonian, of course, we can write out the Schrodinger equation for many electron system, which is a many-body quantum system. So how to treat this many-body system is very challenging because you have this term Vrij here, right? This is the Coulomb repulsion. And the coordinate of I and the coordinate of j are connected to each other. You cannot separate them. That means you can no longer apply the separation variable. If you cannot apply separation variable, that means you essentially have no way to solve the equation exactly, right? So in chemistry, the many-body system, the Schrodinger equation for the many-body system cannot be solved analytically exactly. I should say analytically exactly, it's impossible to solve it, okay? But numerically, if you are willing to, in this course, we will talk about one of such ways to solve the Schrodinger equation. If you're willing to essentially expand your wave function in a power series, if you include enough terms, then numerically, essentially, you can get the exact solution, okay? But analytically, you cannot, okay? So this is obviously very challenging. So what should we do? What we can do is actually by introducing a physical approximation. That is to say, if we assume each electron is moving under a sort of averaged central field, then we can separate this many-body system into multiple independent equations, at least formally independent. Then for each particle, you are doing a central potential problem, right? Then you can use the old method to solve it, right? What does that mean, the averaged central potential? It means, well, for an electron I, it is moving under the potential for this I electron, which is only a function of the position of I. It does not depend on the position of other electrons, at least formally, but as we will see actually, numerically in the detailed expression for this potential, it also depends on all the other electrons. But at least formally, we can write this potential, this effective average potential being a single function, V of R, This is a single variable function. Okay, so you do not have Rij term. You're sort of averaging all the electron-electron interaction. So essentially, you're reducing approximately, of course, this many-body system into an effective single particle problem. All right, this is the key here. So this potential actually depends or is determined from all the other electrons. Ej, J is not equal to I, which means if you're considering the first electron, this potential felt by the first electron is actually determined by the second, third, fourth, fifth to nth electron. This potential is determined by the position of all the other electrons implicitly. Okay? Depend on the n-1 electrons. So explicitly, you can simply write this potential function as a function of the position of ith electron. But physically, this potential is actually determined by averaging the interaction of this electron and all of the other electrons in your system, in your atom or in your molecule. Okay. But of course, you wonder, well, this looks so good, but can you tell me how to actually find such an averaged potential? How to find such an average potential that best represents the real many-body potential? That is, how to find such an optimal potential that captures all the important electron-electron interactions? This is an excellent question. I will not talk about the actual procedure in this lecture because we need more knowledge about quantum mechanics. Especially, we need the knowledge of variation in order to do this. But I think here I just tell you that we can do this. And eventually in this course, we will do this. Okay? I will derive such an optimal potential for you. Okay? So suppose we can do that. Okay? Suppose we have found this optimal potential. And for the ith electron, it's only a function of the location of the ith electron. Then the total Hamiltonian is written as a summation of n terms, right? You have n electrons. For each electron, we use a small hi to represent the Hamiltonian for this ith electron. And this Hamiltonian only depends on the location of the ith electron. So Hi is just the Hamiltonian for the ith electron, which is the kinetic energy for the ith electron, minus for in an atom, you have the electron nucleus attraction and this effective potential. Or I should say the averaged potential, which only depends on the location of Ri. So we can write this, we can combine the next two terms because the next two terms, these two terms are just the potential energy, right? So we can just combine these two terms together to give you kinetic energy of the ith electron plus the potential energy felt by the ith electron. Okay? If you're not comfortable with this idea of the average potential, well, you can just think about, suppose somehow you can find it by spherically averaging the distribution of the electrons and compute the electrostatic potential at a particular point R on the sphere. You can think about this in this way. So of course, this is kind of a hand waving style of really teaching you about this potential, because in the later lecture, we will actually derive the expression for this potential. But here, if you're not comfortable, you can think about this average the potential is just like something 1 over R, okay? Suppose you can, okay, you solve for the, you can solve for the electron distribution, right? Then spherically, because it's an atom, the electron distribution is spherically symmetric, well, right? Then if you add up the distribution, you're averaging all the distribution of the electrons. What does the average mean? Well, that means you integrate over theta and phi. You average over theta and phi. And then you essentially have an average distribution of the electron. In classical electromagnetism or in classical electrostatics, you can calculate, given a distribution of the electron, you can calculate the electrostatic potential at a particular point on the sphere. And that will give you the averaged potential. Okay, this is really a classical picture of thinking about it. This is not 100% correct, but I can, in this lecture, I can only give you such a qualitative description. All right. So by doing this, the Schrödinger equation, which is equal to H plus I, our Schrödinger equation, many-body Schrödinger equation, H plus I is a many-body wave function. It depends on the location of all the electrons, is equal to E plus I. Right? And by doing this, if your Hamiltonian can be written in this way by introducing what we have just said previously, then you can use the separation of variable. And actually in 1928, Hartree proposed a way to do this. Actually, Hartree said, okay, if you apply this central field approximation, then he can use the separation of variable by separating the many-body wave function as a simple product, phi 1, which only depends on R1, times phi 2, which only depends on phi 2, R2, dot, 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 to phi n, which only depends on Rn. So you have a product of each wave function, of each of the wave function that only depends on the position of the ice particle. So this is a product. When we talk about summation, we use sigma. When we talk about product, we use a capital pi. This is a product for n electron system. It contains n terms, and each term is phi I, Ri. Each wave function, each independent single particle wave function only depends on the location of this particle I. Because it is Hartree who first proposed this formalism. Therefore, this separation of variable, this form of the separation of variable is called the Hartree product. It is proposed by Hartree in 1928. It's just 2 years after the Schrödinger equation. So Hartree really is, at that time, Hartree is really the pioneer of this field of quantum mechanics. Okay. And therefore, by plugging this Hartree product back into the many-body Schrödinger equation, we have So the Hamiltonian is the summation of n terms, hi, ri. And the many-body wave function is now, by using the Hartree product, is a product of n terms, right? This is equal to the eigenvalue times the product of n terms, right? And remember, because this Hamiltonian only depends on the position of Ri, so when you do the partial derivative, well, you have Laplacian, right? This Laplacian operator only acts on the ith electron. It will not act on the other electrons. In other words, what you have is essentially, you have n equations, n independent equations. For ith electron, the equation is hi r phi I r is equal to epsilon I phi I r. Well, here you can write ri, you can write ri, but since all the n equations, they have exactly the same form. Formally, they are exactly the same. So you just need to solve for y equation, then you essentially solve all the n equations, because formally they look identical to each other. So here I just no longer write ri here, because formally they all look identical. And r here in the single equation is simply a dummy index. So for a dummy index, I can just remove the index I, okay? But of course, if you want, you can still write ri, no problem, okay? But of course, here, I still write hi, phi I, and epsilon I. This is because I want to emphasize this is for the ith particle. This is for the ith independent particle wave function. And epsilon I is the eigenvalue for the ith eigenequation, right? The point here is Rij is no longer in the equation. This is also the so-called non-interacting picture. Right? You no longer have an explicit term to describe the Coulomb repulsion between two electrons. One electron is moving under an effective averaged single particle potential. This is the key here, okay? But of course, this single particle potential is actually determined by averaging all the other electrons. So this non-interacting doesn't mean there is no interaction. You still actually capture the electron-electron interaction. It's just, it's captured in such a way that it seems there's no interaction. But the physical interaction is captured in this approximation. Okay? And what is the total energy? The total eigenvalue, capital E, is approximately, I cannot really write an equal sign, okay? Approximately the summation of the epsilon I. Well, you wonder why I write an approximate sign. Well, if you plug in this Hartree product in this many-body wave function, many-body Schrödinger equation, yes, indeed, you get capital E is equal to the summation of small e, or the summation of epsilon I. I write approximate sign because this is not actually the entirely correct way to do it. So actually, Hartree, yes, Hartree made a very important contribution, but actually, his separation of variable is not entirely appropriate. That is because he ignores a very important property of the electron, that is the spin. If you include the spin, then the many-body wave function should be written in another way. It's no longer a single product. It's actually a linear combination of multiple Hartree products. And this, each term is actually a permutation of the index of the electron. This is because electrons are identity particles. They are not distinguishable in quantum mechanics, and therefore you should permute the index in your Hartree product, and you should add all of these permutations together. This is your actual many-body wave function. But of course, at that time, at the time of Hartree, perhaps he didn't realize the spin is an intrinsic property of the electron, and the electrons are identity particles. So he writes this Hartree product, which still is a very important contribution historically. Okay, so that's why here I only write approximate sign. Approximately, by using Hartree's formalism, yes, you can have this summation. All right, so I should write an explanation here. The Hartree product, the psi here, is not really correct, since it ignores the effect of spin. And, well, the effect of spin, of course, includes the Pauli exclusion principle. So I should really not say and, but I can just add a parenthesis including Pauli exclusion principle. All right. So in 1928, Hartree did this. After 2 years, some people realized that, well, there is this deficiency in Hartree's treatment. So they further improve Hartree's treatment to get really a correct formalism. This is the work done by Fock and Slater in 1930. So 2 years after Hartree's work, okay? And the formalism nowadays is known as Hartree-Fock theory. It's really the correct way to do this effective single particle picture. Slater's contribution is really about, Slater said, another way, another physical way to view this average potential is really that for a single electron in a bunch of electrons, the charge, the Coulomb interaction felt by this electron is actually somewhat screened. So he proposed that you will have a screened charge. This is screened or effective nuclear charge. You have a screening effect. Yes, the nuclear charge is positive too, for instance. But because the existence of another electron, somehow this Coulomb interaction is screened. This Coulomb attraction between this electron and this nuclei is somewhat screened by the other electron. So you don't have really two here. You really don't have two. You have, say, 1 point something. It's less than 2. This is really the physical picture that Slater introduced. All right. And because this is only of historic importance, we won't talk about the details. All right. So for multi-electron atom, under this Hartree approximation, by using this Hartree product, so phi I R can really be written as the radial part times, again, the spherical harmonics. The spherical harmonics is exactly the same, right? This is the same as the single electron atom. That is the hydrogenic atoms. It's the same. They're exactly the same, okay? It is the radial part that's different because radial part depends on the actual functional form of the central potential. So this is, of course, the potential dependent. Okay. So our task is really about the radial part. It's not about the angular part. Angular part is very clear. It's the spherical harmonic. Okay. And this R and L in a multi-electron atom. So for atoms, actually exact, or I should say again, numerically exact solutions are available. However, these are not really particularly useful for practical calculations for molecules. If you want to study how atoms combine with each other to form a molecule, then it's not really practically useful. But for atoms, the numerically exact solutions are indeed available. The common practice is actually we can use approximated atomic orbitals as basis. That's the common practice. These atomic orbitals are mathematical functions constructed by the chemist with good properties for the computations. Okay, they are these atomic orbitals. Atomic orbital is abbreviated as AOs. Atomic orbitals are for practical computations. You should, of course, add good properties, right? For instance, what are the exact behaviors for this exact solutions? If you can, you should add more good properties into these mathematical functions, right? So that this approximated mathematical atomic orbitals are really resembling the exact physical solution, right? But sometimes this cannot be done. Sometimes we actually construct the functions actually by satisfying several exact properties, but not all of them. Because otherwise, we cannot have a really efficient and fast computations. When I say computations, I mean you really use those atomic orbitals to calculate molecular integrals. And if you have a well-designed mathematical function, these integrals can be expressed analytically. Okay. They may not, I should say, they may not have the exactly correct physical behavior around some regions. So in a practical molecular quantum mechanical calculation, the atomic orbitals are mathematical functions. They have, of course, certain physical character. They have certain physical origins, but do not take them too seriously. Do not think them as the physically exact solution of an actual many electron atom. They are not. They are mathematical functions constructed for calculation. They have some good properties, but sometimes they do not have the correct physical behavior in some region, not all region, but in some region. For instance, around the nuclear, they don't have the correct behavior as what you will have for a physically exact solution of a, for instance, hydrogen atom. Okay, but this is not really this is not, I should say, not really an issue. Since you will use a linear combination of them, actually you will, since we use a large number of bases with the coefficient to be optimized. Actually, we use a large number of bases. These bases are usually flexible enough so that you can, by varying the coefficient, you can actually have a very good approximation to the actual result. Okay, to the actual exact solution, I should say. You will optimize those coefficients anyway. Okay. All right. So next, I will talk about several very useful atomic orbitals that we use in actual molecular quantum mechanics calculation. The first type of orbitals or mathematical functions I want to introduce is the Slater function. Or you can call that Slater type orbitals. It is abbreviated as STOs. They stand for Slater type orbitals. The mathematical function we use is, again, we're talking about the radial part. The angular part is just the exact spherical harmonics. There's no question about it. Okay. So what we're approximating is really the radial part. STOR is 2 lambda 3 over 2 over square root 2n times 2 lambda r to the n minus 1th power exponential negative lambda r. Lambda is just a parameter. If you let L be equal to n minus 1, right, according to what we have in the hydrogen atom, then you can rewrite this Rn STO as RL STO. This is 2 lambda 3 over 2 over 2L plus 2 factorial square root times 2 lambda r to the L's power exponential negative lambda r. If you look at this part and you compare with our exact solution of the hydrogenic system, this actually partially resemble the hydrogenic radial function. So it contains certain physics, actually. Furthermore, if you look at actually 1s, so the atomic orbital, of course, let's use another notation. Usually we use chi to denote the atomic orbital function. NLM, STO, this is STO type function or Slater type function. This is the radial part times the spherical harmonics. Now, if we fix this lambda, this parameter, to be equal to z over n, okay, then what is our 1s STO? The 1s STO, or I should say when n is equal to 1, okay, this is equal to R1s. This is exactly the exact solution for hydrogenic system. This is the exact solution. Okay, so you see, this Slater type function really captures at least partially captures the correct physics. For 1s, it's exactly equal to the physical solution. If you do a linear combination of n is equal to 1 STO and n is equal to 2 STO, this will give you R2s. Again, R2s is the exact solution. So you say, oh, so actually, if you just put n be equal to 2, the STO is not the exact solution for the 2s. But if you are willing to use a large number of atomic orbital, or in other words, you are willing to use a large number of mathematical functions, then, well, in this case, it's really not a large number, it's only 2, right? Then you can construct the physical solution, right? In this case, if you combine n being equal to 1 and n being equal to 2, then you have 2s. Okay, so if you care about ns, right? Not 1s, 2s, but 3s, 4s, etc. So then you need a large number of the combination of the Slater type orbital from 1 to n. I use n prime here because here I already have n. N is a particular number. For instance, if you want to do 5s, then n is equal to 5. You will have 5 terms in the summation. And the coefficient, of course, is just an inner product. Dot Rn prime STO. Okay, so you will have a linear combination of the STO to give you the exact physical solution for the NS state. All right, so you're thinking, wow, this looks pretty good. So basically you can get the exactly correct. Does it mean the STO capture all the correct physics contained in the exact solution? Unfortunately, the answer is no. However, for instance, let's just see one such property. Okay, one such property. Let's calculate the expectation value by using the STO. This is the expectation value. This is, well, you just evaluate the integral. It turns out this is equal to 2m plus 1 over 2 lambda. here we set lambda is equal to z over n, right? Here we set lambda is equal to z over n, as in the case of hydrogenic system. For hydrogenic system, the expectation value is 1 over 2, 3n squared minus L plus 1 over z. Of course, this is atomic unit. So you see, the expectation value given by Slater type orbital is not quite physical, right? Yes, you have n squared behavior because lambda is z over n. So essentially, you have an n squared behavior, but it's not quite right, right? So of course, then what you need to do is, of course, you should not use a single Slater type orbital, right? You should use a linear combination, right? As what we have previously illustrated here, right? We have this 3 example here. So you should introduce, another way to say this is you should introduce flexibility in representing the physical radial solution, right? How to do this? Well, in general, if you want to target at R and L, this is the physical solution or the exact solution, or for a many electron system is the numerical solution, numerically exact solution for a particular kind of atom. This is important. For different kind of atom, you should have different linear combination, right? That's why for different atom, you should choose different atomic orbital bases. Okay, they are all constructed by using this elementary Slater type orbital, but you have different linear combination coefficient. Okay. So your target is this. You're trying to approximate this numerically exact solution by using Slater type orbital. You should really do a summation. This is a really double indices summation to Kasai z m prime L prime dot R m prime L prime STO R. And well, this STO function is a function of R, that's right. But its actual value depends on the parameter you specified, right? So I also write in this way, that means this function actually depends on the actual parameter you use, right? So you can introduce the NL dependence for the parameter. So this parameter becomes already a fitting parameter, right? Kasi is your choice. This is your choice. How many terms do you want? Well, if you are willing to use only 3 terms, yes, you can get a set of the optimal coefficient, right? You can get a set of this is the expansion coefficient, right? You need to be, well, this is again a set of the fitting parameters, right? You have a targeting function. This is your targeting function, and you use a linear combination of the Slater type orbital. Slater type orbital is already well defined, right? Well defined, and then you just use this boundary function to approximate this targeting function. So this is just a fitting procedure, right? Kasai depends on how many terms you want to use. If you only want to use 3 terms, yes, you can do that. You can get a set of the optimal coefficient based on the 3 terms you're using. But maybe the result will not be too good, especially if you want to approximate, say, a quite complex, a quite complicated radial distribution, right? For a atom, for instance, for instance, for a transition metal atom, it's pretty complicated. If you if you are willing to use 3 terms, you can get what you want, right? But maybe it's not the optimal case, right? If you want to use 6, 8, or even 10 terms, yes, maybe your result will be better and better because you are introducing more and more flexibilities, or you're introducing more fitting parameters. Then yes, you can get a better fit, right? You will get a higher quality of your basis, right? Okay. So of course, as I said, this is really a fitting procedure. How to do this fit? So what you are doing is actually minimizing. So you simply do this inner product. So this is your exact solution, numerically exact solution, minus your approximation. And you do this inner product. All right. So basically, it's the magnitude of the difference between your target and your approximation. Of course, you should try to minimize that, right? Minimize the difference. Well, if there's no difference at all, then you get exactly the right answer, right? But usually, you will have some difference, of course, especially when you're only using a few terms, okay? So you're minimizing this inner product with respect to what? What are the fitting parameters? Well, you have C, right? A set of C parameter. You have a set of lambda parameter, right? So, right? So you're just changing the value of C. You're changing the value of lambda. You have, of course, a set of C, a set of lambda. Then you just see, okay, which set of parameters give you the lowest value for this inner product, which means which set of the parameters give you the closest result to the actual exact solution, right? That is the fitting procedure. Of course, if the function is pretty single, then you can derive an analytical expression for the fitting, the analytical expression for the fitting parameters C and lambda. For instance, if you're doing a simple linear fitting, right, least square fitting, then of course you can derive the symbol expression. But of course, in general, this is a nonlinear fitting procedure. So you have to use computer algorithms to help you to do this fitting. There are actually multiple algorithms available for this kind of fitting. In other words, actually, this is a optimization problem, really. You're doing this optimization with the constraint, of course. What is the constraint? The constraint is, well, you should always have the normalization, right? Of course, in calculus, we have learned how to do this, how to minimize a function with a constraint. You should use a Lagrangian multiplier, right? All right. So I will not talk about the details about this fit because it involves the actual computer algorithm. And but you know at least the big picture about how to do this fit. And you know that yes, indeed, by introducing more and more flexibility in your fitting function, you can essentially get a very high quality basis. But of course, if you use too many terms, the Cassie here, this Cassie, if this Cassie is too large, for instance, if you use 30 terms or 20 terms, This is a very large number. This is a very large number of terms. Of course, you will get a very high quality basis, that's for sure. But this kind of basis is not really practical in an actual calculation, because then in order to do the molecular integrals, you need to use this basis to calculate the actual integrals, the electron integrals. Then you will need to calculate too many terms of the integrals. Actually, the number of integrals is I will not say it's corresponding to number of bases, because that depends on the actual level of theory you're using. If you're doing Hartree-Fock, for instance, the computational cost is proportional to the number of bases to the fourth power. If you're doing Hartree-Fock, its computational cost is proportional to n to the fourth power. N is the total number of bases in your system. Then if you say you use a very high quality basis, then your calculation is going to be very, very expensive. And usually you don't need to do that, because first of all, the level of theory or level of the approximation you're using has its intrinsic limitation. Its accuracy is that much. No matter how you improve your basis, you're not gonna do better than the intrinsic error of your approximation. So there's no point of wasting your computational time to do a really extremely high level basis. It's really a waste of time. So you should pick a balanced basis. For instance, if you use, say, in this case, for instance, you use 5 terms or 4 terms, maybe the results are good enough. When I say good enough, I mean at that level of approximation, it's good enough, right? So quantitatively, how to say whether or not your result is good enough at that level of theory, this is actually called the basis set error. You simply do multiple calculations, right? You use a small basis, an intermediate basis, a very large basis, and then you can see if the number actually you got from different bases start converging, right? When you increase the size of the basis, the numbers start converging. Then you know, basically, I can stop at here. I don't need to go to higher level of the basis because my numbers are converging. All right. Okay. So Kasai is, in principle, again, in principle, we want the Kasai to be large enough so that the linear combination resembles the exact solution. But of course, you need to consider the computational cost. So you need to have a balance here. All right.